Right. Yeah. So last week you already discussed about some basic things on how, like, the three components of ML, the basis of ML, and these were the data, the hypothesis space, and the loss function. So you discussed what are the attributes of data, like data point, features, labels, what these are, and then the intuition behind choosing a hypothesis space. So that the hypothesis space is a set of different functions. For example, it could be like linear functions, so all straight lines, or it could be all polynomials of second degrees. Yeah, so that's the hypothesis space. That will be the function that will try to model your data, and that's why this is sometimes called model, but the model is actually when we feed the function to the data. So, but yeah, in any case, you will, like, if you Google it online, you will see these two being mixed, the hypothesis space and the model. But yeah. And then the intuition behind the need of a loss function. So, like, we need to be able to tell how good our model is, and that's what the loss function does. It's a way to quantify the performance of the model. Yeah, and then in the round one notebook, you show the basics of sklearn, how to instantiate a class, how to fit a model to your data, and then how to use that fitted model to predict the labels of new data. And this last part is also called inference. So you may encounter that term online. Yeah. So about this week we are going to focus on regression. So what is regression? It's the set of ML problems that tries to predict a continuous value as a label. So for example, in round two, maybe you have already checked, but the goal is to predict the price, if I remember correctly, of some houses. So like the price can be any positive real number. So yeah, there are infinite, in a way, number of possible labels. And yeah, so another example is predicting the temperature of the next day and so on. And the goal is to learn a hypothesis map h of x by minimizing the average loss incurred on some labeled data points. So these labeled data points are data which we must have already acquired. Yeah, and then what sets regression methods apart from classification methods is the choice of the loss function. So the function that quantifies how good our model is. And yeah, in a higher level, the difference is that in classification methods, the labels are always a finite set. So for example, is this picture a cat or a dog? That's classification problem. Yeah, so the learning goals for this week are formulate regression problems by identifying the data points, their features, and the labels. So you should be able to make the distinction between those three. It's not always so clear, and it can be tricky sometimes, but yeah, you will see an example in this round. And then you should learn how to represent the features and labels of data points as NumPy arrays. So NumPy is a library in Python that's used for array manipulation. Yeah. And then learn how to use linear regression methods with Python's scikit-learn. So yeah, this one I previously called sklearn. It's actually the same thing. Scikit-learn is also called sklearn sometimes. Yeah, and then test the effect of varying number of features on the training error, and test the effect of varying sizes of training data on the training error. More on that we will discuss later. And then learn some statistical and computational properties of the squared error and the Huber loss functions. So yeah, do you have any questions so far? Did someone say anything? Okay. Yeah, let's go to the contents of this around them. So what is linear regression? Um, it's like a sub problem of regression problems, and the hypothesis space is a linear combination of the features x and some weights w. And the role of this function is to take some features and output a prediction y hat. So this is like x is a specific example and y hat will be a specific label, like a specific prediction for this example. Yeah, and the WIs are called weights usually. And so they kind of measure how important its corresponding feature xi is. Yeah, and W0 is known as intercept, but you will also encounter it as bias. So these two terms are used interchangeably. Yeah, and yeah, so yeah, the W0 just specifies where exactly will the line cross the x-axis, for example, if you imagine this in a two-dimensional scale. Yeah, so how can we find the best hypothesis? Uh, yeah, so that's where loss functions come in, and we want to minimize the loss function of like the difference between the real label y and the predicted label y hat. So yeah, the loss function quantifies this difference. And for a set D, so this is a whole data set, 10 points, we can evaluate the fit of the hypothesis function um, by calculating the average loss. So yeah, we just calculate the average of the loss function, and the loss function is the choice of ours. And now we are going to talk about the squared error loss, which is probably the most commonly used loss function for regression problems. And it's also the simplest one. So yeah, it just takes the square difference of the prediction and the true label. Um, yeah, so sorry about this. So inserting the squared error loss into the previous function we saw, the average loss, we get the mean squared error, which is abbreviated as MSE. You will also see that a lot when Googling related stuff. So yeah, if you expand it further, you will just end up with this formula. It's pretty straightforward, but in Python, you have that already implemented, so there's no need to implement it yourself. Yeah. And then to choose the best predictor, we need to minimize this function. So we are going to pick the function 8 that belongs to this hypothesis space where the average loss is minimized, which actually corresponds to picking the weight W for which the average loss is minimized. This is equivalent since the Y and X are like constants, like they are data, cannot change them, and W's are the weights which need to be modified so as they fit the data in the best way possible. Any questions about linear regression? I guess this is also discussed a lot in the notebook. Like I have mostly copy pasted the theoretical background from the notebook, so you can always go back to that. Yeah, and then there were questions such as what's the effect of the size of the training data on the training error? And well, How is it possible that when we use more data, we sometimes get bigger training errors? So these are kind of like corner cases. Yeah, yeah, that's it from the slide. So if you don't have any questions still, maybe I could go through the notebook, but um, if you have any questions, go ahead now. Okay, then. So this is the notebook. At first, you have some theoretical background of what regression methods are. Um, then the learning goals, which are pretty much the same as the ones we discussed. And here is the problem which you will have to solve. So you have this data of real estate investment funds of 20 different neighborhoods, and yeah, so you have the average number of rooms as the features, um, and sorry, so yeah, each data point has information about the average number of rooms, the percentage of buildings constructed before 1970s, yeah, 8 experimental features, and the quantity of interest. The label is the median house price for a neighborhood. So this is kind of a common regression problem where you have to predict a price of some sort. Yeah, the data. So the features are usually denoted by X. X capital is the set of all features. So for the whole data set, for all of the endpoints. And in most cases, when you see a small x, it means just a single data point, a single set of features. In this case, it will be a single neighborhood. Um, yeah, and then the label vector is just a vector which has the price for each neighborhood. Okay, so to load your data, you are going to use the pandas library, which is pretty straight, makes it pretty straightforward. Like just use a read CSV function. Um, yeah, that's already implemented for you. Then you also have a basis of how to plot your label. So in your case, since you're only using the the first feature is the average number of rooms, and then you're trying to plot it against the median apartment value. So you'll have like a 2D plot here, and so on for the other features. And then we go into linear regression. We pretty much discussed all this, so I won't go into further details. Let's see the code though. So yeah, here we instantiate a model of linear regression. You have already seen in round one how this can be done. And then we fit the model. So that means that we actually minimize the average loss function, the one we saw before. This is already implemented for you. You don't really need to do the minimization yourself. Um, yeah, and these are like the optimal weights that you found. Then, since we use a mean squared error, then we can use it in order to see how good the model is. For example, we could compare it to other models. So yeah, the training error is the mean squared error based on the true labels and the predictions. Yeah, yeah, and then pretty much it's all that you like the rest is the things that you have to solve. I'm not really sure if I should go into any further details about that. These are just programming tasks. But of course, if you have any questions, then go ahead and I will be happy to discuss this now. Yeah, and here are the two questions that we uh, briefly discussed. So how the number of features affects the performance of the model. And here you will see that when we use more features, we get a better empirical error. And then like you have to think about why does that happen? And then how does the number of data points affect the training error? And here you will see something that you probably don't intuitively expect. So with 10 data points, we actually get a worse performance than with just one data point. But well, if you think about it, it kind of makes sense. Yeah, yeah, because like with one data point, we can just learn that data point. Like the there are infinite lines that can pass through a single data point, so we can always fit a single data point. Right. Um, yeah, and then there is some talk about how to handle outliers. So outliers are data that do not seem to follow the common distribution of the data. Um, yeah, we don't really have an example here, but for example, if one price would be much higher than the others, then that would be an outlier. And like if we use the common methods in linear regression, then the result would be skewed because that single outlier would make the line go like upwards because it's like the difference between the other data points is huge. So the line would be pushed more upwards. But we don't really want that. We probably want to minimize the effect of these outliers. And that's where the idea behind Huber loss comes in. Um, yeah. So this is the loss function that that it has to minimize. And it's a bit different than the classical linear regression one. But again, this is already implemented for you in sklearn. Oh, yeah, here it is implemented in this stuff. Yeah, I don't really have anything else to discuss. Um, I will wait a minute for questions. Yeah, maybe if you don't want your question to be recorded, you can ask it after I start recording. That's also fine. Yeah, what else? So I'm also almost always available on Slack, so you can always contact me there, either in a PM or in the general chat. Uh, yeah, with any sort of problems, even if it's just programmatical ones or problems with Python, with how to use sklearn and stuff. Yeah. So if there are no questions, I think I'm gonna stop